Okay, here we go. So,
Quickly
quickly review what we started
It's
talking
not
about
straight down.
yesterday.
It's past straight down where it's coming back, is it?
Can't do that.
You can if it's on a round surface.
Yeah, you can if it's earthquake.
Or if it hits a wall.
We don't know that yet.
It hits an elastic wall and slowly changes, but it.
Oh yeah, that's what we were doing. Most important thing in geometry.
I wish I knew what this meant. I'm having a really hard time though.
Sokotoa?
Sokotoa.
You don't know what that is? We went over.
Well, let's just say I have really bad memory of important stuff. SCT. What about it?
Sine cosine.
Okay, so real quick. So SOHCAHTOA, this summarizes everything we need to know about right triangle trig. Right, it tells us that if this is the angle we define as theta in this right triangle, the hypotenuse is always determined because it's opposite the right angle. But then the side that the angle looks at is the opposite side, the side it's next to is the adjacent side. And so this defines these trig functions. We know that sine of theta then is defined as the ratio of what? Opposite over hypotenuse. Cosine theta is the ratio adjacent. And when I say opposite over hypotenuse or adjacent over hypotenuse, we mean the length of those sides. Right, that's what we're talking about. And then tangent is the ratio of the length of the opposite side over the length of the adjacent side. So for example, if I have we always use 3, 4, 5s. How about if we use a 5, 12, 13 triangle? And I'm going to call this theta. Okay. So what is the sine of theta in my triangle diagram? 13. Opposite, good. Opposite over hypotenuse, so 12 over 13. Good. What is the cosine of theta?
5 over 13.
Good. Adjacent divided by hypotenuse, and tangent.
12 by 5.
Okay? Make sense? So, first things first then. Let's take an example where we're given a vector of a given magnitude, and we want to, and an angle, right? And we want to break this into components. Okay? This is what we just started talking about yesterday, right? We can always break any vector up into orthogonal components, meaning right angle components. Just a word about that. The importance, why is it that the components have to be at right angles? Well, okay, but there's something else going on here. Like if
It's in line with the XY.
like we would use, for example, x and y components. Why would we break it into x and y components? Why do we break it into, I don't know, let's call it something different. Why do we break it into like a u component and a v component? Well, it wouldn't, I mean, it doesn't, that wouldn't, I mean, but what's wrong with that picture?
It's not perpendicular.
They're not perpendicular. Why is that so crucial, though, that they're perpendicular?
So that they don't interfere.
Oh, okay, so that they're independent of each other, right? Is there a component of this v vector in the u direction? Yeah, there is, right? If I took this v vector, let's say I take a vector from there in that direction, that's going to have, I could break that into components that look like that, couldn't I? It's got a component in the u direction. If I cast a shadow straight down on V, well, excuse me, if the sun is directly above you, the V-axis is going to cast a shadow, which doesn't work, right? They're not independent of each other. But here, they are. If the sun is vertically aligned above the x-axis, well, the y-axis casts no shadow. There is no component of y in the x direction or vice versa, right? Does that make sense? You can't think of a way. If I have a vector in the y direction, there is no way to write that as a component, having a component in the x direction, right? You can't. Because if I go in the x direction, then I can't, I have to have a non-orthogonal vector that goes back in the y direction. See what I'm saying? So it doesn't work. It doesn't work. The vectors have to be, the coordinates directions that we assign have to be perpendicular to each other, orthogonal. Okay? All right, so x and y. So what do we do here? You tell me, what am I going to do?
You're gonna take sine 23 and multiply it by 2 points.
Okay, maybe let's draw a picture first. How about it? Okay, so we've got a vector v. It's at an angle of 23 degrees. So that's, about like yay, something like that. Okay, there's vector v. There's vector v, right? Okay, we know the magnitude. What does that correspond to in terms of the vector? Meaning length. Okay. So the magnitude is 3.7. Run out of virtual ink again. Twice today. Oh, it's gray. That's fine. See that very well. Okay. And the direction. How is the direction described?
Angle 23 degrees.
From the positive x-axis. So in what direction do we reckon angle, increasing angle? Clockwise or counterclockwise? Counterclockwise, right? So from the positive x-axis, we're going to sweep out angle in this direction, right? 23 degrees worth of that angle, right? Does that make sense? Okay, so if I want to break this into components then, is my vector, what part of the right triangle that I'm going to create is my vector always going to be? The hypotenuse, right? So we're going to break this up into pieces. We're going to break this up into a horizontal piece and a vertical piece that are orthogonal to each other, right? So if this is the vector v, we could call this one v sub x, meaning the x component of v. And what are we going to call this one? V sub y. Okay, and then we're just going to solve for those how? SOHCAHTOA. Right, exactly, SOHCAHTOA. So let's define kind of a shortcut for ourselves in using SOHCAHTOA, though. What can you tell me? Well, okay, so let's find v sub x. The length of the hypotenuse is 3.7. That's known, right? So what's going to be the SOHCAHTOA relationship that we're going to leverage here to solve for v sub x? Cosine, right? Because if this is my angle, that's my theta, then we want to invoke the relationship between the adjacent and the hypotenuse, right? So that's cos, right? So we've got cosine of theta, which is, in this case, 23 degrees, is equal to the ratio of, v sub x divided by the hypotenuse, which is 3.7, right? Okay. What am I going to do to solve for v sub x? Okay, I'm going to multiply by 3.7. Now, this is where I think you can take a logical shortcut when you're doing your work. So that's going to give me, when I isolate v sub x, I'm just going to get 3.7 times the cosine of 23 degrees. Okay, now especially those of you who have had trig. If you haven't, it's okay. I mean, we're not going to do any really high-power trig here, but what is the range of a cosine function? The outputs always lie between 1 and -1, inclusive, right? But 1 and -1 would just be for the 90 degrees and minus 90 degrees, and those are pretty easy ones to deal with anyway, right? If I have a vector that's already lined up in the x or y direction, I don't have to do anything to break it into components. I already have the components, and we'll see that in a second, okay? So you know that cosine is always going to be pinched between -1 and 1, and for any non-right angle value, non-multiple of 90, that means that the output is always going, its absolute value is less than 1. When I multiply by a number whose absolute value is less than 1, what does that do to the result? Does it make it bigger or smaller? Smaller. Smaller, right? So multiplying by a cosine is always, or a sine, same thing, right, is always going to give us a value that's smaller than what I started with. What's always going to be the longest side of this triangle? The hypotenuse, right? So if I'm solving for one of the shorter sides, does it make sense then that you don't have to necessarily always show this step, because you know that you're going to be multiplying the long side, the hypotenuse, which is the magnitude of the vector, times whatever the SOHCAHTOA relation is that links it to the component you're interested in, right? I'm going to start with 3.7, and it's got to be smaller because I'm finding a component of a vector, right? And so I'm going to multiply in this case by the cosine because it's the adjacent component, right? The adjacent leg. Make sense? And so that's going to give me an answer, right? How am I going to find v sub y? It's going to be sine, isn't it? So for v sub y, did everybody get what I was saying about the, sometimes people are just unclear. So if I divide by cosine, we can set up this relationship, but does that make it clear that you're always just going to multiply the hypotenuse by either sine or cosine if you're finding the x or y components, right? Because that makes it smaller like you want to. Okay, so then v sub y would just equal the hypotenuse times, I'm going to make it smaller by multiplying by, in this case, the sine, because it's the opposite, right? I want to relate opposite and hypotenuse, so that's sine's job. And I would just crank those out in a calculator. So let's do that. If we, in either Desmos or on the graphing calculator, what do you suppose one of the most common errors people make is? Radians versus degrees. Okay. So we're using degrees here, right? So we got to make sure the calculator's in degrees mode. So we're just going to go mode, and it's in radians. So I got to go down, flip that over to degrees, and we're good. Okay, so now I've got 3.7 times cosine 23 degrees gives me about, how many sig figs can I keep here? 2. So what's that give me? 3.4, right? And then if I want to do, sine, look what I can do. I can just go back up and grab that previous calculation, hit enter to pull it down to the edit bar, and then if I hit second left, it takes me all the way over. I can just go to this cosine and override it with a sine. So there it is. So what's that one rounded to my 2 sig figs? 1.4. Okay. Okay, and let's check ourselves. There they are, 3.4, 1.4. Those are the answers. Okay? Straight from Moodle. All right, so how about this one? A little different. Right? So what about this time? What am I going to do differently here? Well, let's just draw the picture first before we start talking about it in detail. So. Where's this going to go? If this is the positive x direction, right, and this is the positive y direction. What is an angle of 151 degrees is where?
In the
Second.
Quadrant 2? Okay, because this would be 90, and that's going to be 180, right? So it's about there-ish, right? Okay, so something like this. Okay. And then that's telling us that this angle right here, all the way around like that, is 151 degrees. Okay? Now I want to show you a couple cool ways to look at this. You just have to be consistent. You can do this any way you want to. Okay? So, first of all, we define SOHCAHTOA in terms of an acute right triangle, right? So this triangle right here is not really helpful to us, is it? Right? What triangle are we probably going to use instead? We have two choices.
Use the X, have the X be the bottom, and then draw a line.
Okay, so we could say if we know that it's 180 clear over to here, and this is only 151, then what's the measure of that angle right there? 29. Okay, so we could, if we wanted to, we could write this is our angle. So we could use that angle, right? And then break the vector up. What's the magnitude of the vector? 8.8. And we could break it up into these x and y components, right? So we'll call this one v sub x and this one v sub y. And how would those be defined in terms of SOHCAHTOA stuff? So v sub x would equal what? Okay, it's going to equal cosine, okay, but times, we're going to start with the length of the long leg, the hypotenuse, sorry, the vector times cosine
Times -1.
29 degrees. Okay, good. Times -1. How come?
Because we're in the negative.
Okay, good. Because it's the x component is pointing in the negative x direction, right? So if we were going to, for example, if we were going to start a table, and this is where I want to end up today. If we were going to start a table that we were going to use to combine a bunch of vectors, we could make 3 columns in our table. We could have a column that corresponds to the vector, which we'll just call, well, ours is going to be v, and then we're going to have an x component column and a y component column, right? So vector v in this case was broken up into one component is negative 8.8 cosine 29 degrees. Okay, that's going to be the x component for vector v. What's the y component going to be? Okay? Positive or negative?
Positive.
Positive, because it's going up in the positive y direction. Okay? What's another way we could have done it? What other angle could we have used?
61 degrees.
Could have used 61, right? Going from 90 up to 51 is a 61 degree angle, right? So I also could have written this then, v sub x as what? Negative
8.8 sine.
See what I'm saying? We could have broken this up into a y component there and an x component there. Remember, the vectors, the components, have to add like vectors add. Head to tail or tip to tail. right? So whichever one we put first, it doesn't matter. We could put the x component first and then add the y component to the head of the first vector or the tip of the first one, right? Or we could start with the y component first and then add the x. Doesn't make any difference, it just defines a slightly different angle, right? But guaranteed, 8.8 sine 61 degrees is equal to 8.8 cosine of 29 degrees. Okay? And 8.8 cosine 61, cosine 61 is equal to sine 29. Okay? All right. Okay, here's the other trick though. This, you got to be careful with this one. The other trick is you could use the whole angle 151. Now I'll explain this, and then use this one with caution, but it's actually a pretty cool way to do it. And do you remember doing some of this stuff last year? A little bit? Vaguely? Okay, I bet you didn't learn this trick though. This is a pretty good trick. So if we use the whole angle, let's use a reference triangle, we call this, a dummy triangle. That's not going to be at all accurate, right? The dummy triangle is always going to be in quadrant 1. So if we define the dummy triangle here, it looks like this. We've just got some random angle theta, right? And the x component is always going to be defined in terms of the cosine, right? It's going to be, whoops. So if we say that the magnitude of this thing is just v without a vector hat, right? So that just means if I put the vector, it's no longer just a number, but this is just the magnitude of the vector. So v sub x is always going to be v cosine theta, and v sub y is always going to be v sine theta. Well then, if that angle extends beyond 90, the math gods are throwing you a pretty good shortcut here. Because look what happens. If we say v using this alternate way of doing it, if v is positive, in this case, positive 8.8 times the cosine of 151, what sign does the cosine of 151 have? SIGN sign, not SIN sign, right? The SIGN sign of cosine of 151 is negative. It's going to take care of the signs for you, right? And then over here we can define this as 8.8 sine 151, and the sine of 151 is positive. I'm going to get the same numbers either way. That make sense? Okay. But if you use this kind of the shortcut method, you always are defining your components in terms of the x component in terms of cosine and the y component in terms of sine. Okay? All right, so next step is, let's do a real problem. Okay? So we got something like this. We've got an airplane flies due north with an airspeed of 203 kilometers per hour. Okay? So that's its speed relative to the air, right? A wind blows at 64 kilometers per hour to the northeast relative to the ground. Okay? Now I want to show you a little trick here. If we want to write these vectors using subscripts, we could say the airplane flies at 203 kilometers per hour relative to the air. So one way to say that is the velocity of the of the plane relative to the air, right? Does that make sense? V sub PA plus the velocity of the air relative to the ground equals what, you suppose? The velocity of the plane relative to the ground. See how that works? If the inside subscripts match up, that's going to be the common medium that's relating the plane to the ground, right? The plane's related to the air and the air is related to the ground. See what I'm saying? That's the way you can always kind of keep that straight. So that gives us velocity of the plane relative to the ground, right? Okay, so what about that? The plane's flying due north. So if I wanted to break the velocity of the plane up into components. Let's call the plane P. P for plane, okay? So what is P sub x without even doing any math? Oops. What is P sub x? If the plane is flying due north, superimposed, this is x is east, right? Y is north. So we'll use x and y components here. So x really means east, doesn't it? What's the east component of a plane that's flying due north? 0. 0. Right? How about P sub y? 203, right? That would be, I don't even need to draw that, do I? Right? If I did, here's what it would look like. My vector P, just does that. There are no, I mean, there is no x component. It's only a y component, isn't it? Okay? So let's start a table then. We'll start our table here. So we get a column for the vector, we get a column for the x component, and a column for the y component, right? So for vector P, the x component is 0 and the y component is positive 203. That one was easy. What about the air though? The air is blowing at 65 kilometers per hour to the northeast relative to the ground. Okay? So what does that picture look like then? I'm going to recapture this board space for the air vector because the plane vector was simple. What's that going to look like? 45, so we've got, so that's, we're going to call that vector A, and that's a 45-degree angle. Well, the magnitude of vector A was 64, right? And so if I break this up into components, what are my components going to be? From that picture, what is A sub x going to be? 64 times, if that's my angle, I'm doing the x component, what is it again? Okay, good. And we're getting that either from the proportions of a 45, 45, 90, or just by knowing what the cosine of 45 is, right? I'm going to actually write it in terms of a cosine here. You'll see why. A sub y would be 64 sine. Okay, why is this column so great? What's the column doing for us? Yeah, really, think what we're doing here. If we add this vector up, if I draw this picture over here, right? Let's add these components up. We've got 0 component, x component of the plane. The plane's going to go due north. The air vector is going to go over a little bit to, air relative to the ground goes over to the east and by the same amount up to the north. Right? So what if I just rearrange those? Okay, what if I rearrange those so all of the horizontal components are grouped together and the vertical components are grouped together? Because one rule about vectors is it doesn't matter the order in which you add them up. You can freely take vectors and slide them around on the plane. You can translate them as long as when you add them up, they end up being tip to tail, right? So how about if we take this guy here and let's move him over here and this guy up there instead, right? What does that do? Maybe I can be really tricky. Oh. Too much math. So then we end up with there we go. So I'm going to put that a sub y up here. And I'm going to move this guy up there. And if tell me my resultant vector, which looks like this, if that's vector R, what's R sub x? Just that piece, isn't it? Right? So R sub x in this case is just A sub x. What's, just because, sorry, I messed that up, that's P sub y. Just because P sub x is 0. What's R sub y?
A sub A plus.
Yeah, P sub y plus A sub y, right? If we add those vectors up tip to tail, isn't that what we just did in the table? Right? The x component, there is no x component from the plane, we just get A sub x. For the overall, the resultant x component. The resultant y component is the sum of those two. And so we'll come down here, and we could attach some numbers to these, right? Does that make sense? So on the calculator, let's go to the calculator, and let's figure out what those components are, right? So 0 plus 64 cosine 45. So let's go 64 times cosine 45 is that number, and I'll leave it on the calculator. I don't want to round it, because I'm going to use it, right? So that's the x component of the resultant vector. Okay? What's the x component of, or the y component? I'll go up and grab the previous result, and I'll recycle it, make it assigned, and then add to it how much? 203. So there's the y component, right? Unrounded. Okay? So now what? If I want to draw the resultant vector, how am I going to do that? Okay, well, the vector has a magnitude of 248.25, or sorry, it doesn't have that. That's the magnitude of just the y component. I'm going to go over in the x direction, 45.3-ish. I'm going to use the unrounded calculation, though, right? And I'm going to go north that far. Right? How would I find the overall resultant of the whole thing, the magnitude of the whole resultant then?
Pythagorean theorem.
Pythagorean theorem, right? Because this is a right triangle. Okay, so we're going there to there, and I would know that the magnitude of the resultant is just going to be the square root of that squared plus that squared. Does that part make sense? Because we know for a right triangle, if that's A and that's B and that's C, C squared equals A squared plus B squared, so C must equal the square root of A squared plus B squared. That's calculator work, right? So we'll come over here to our calculator, and we can do all this stuff on our calculator. We'll just do a square root of that number squared plus that number squared. Right? And I think it's really important to learn how to use the calculator properly with sig figs. So I haven't rounded anything, have I? If I hit enter, that's my answer. Okay, that's the magnitude of the resultant. Okay, so how many sig figs do we get to keep on this problem? We go back and look. Looks like 2, doesn't it? So what is that number to 2 sig figs? 250. Okay, so part A, okay, no problem, right? Okay, what about part B? How are we going to get this is the part that we haven't talked about yet. This is what I hope, if we can get through this, This is awesome. Okay, this is where I was hoping to get today. I thought this was ambitious, but I think we're going to do it. So we want to define the angle in degrees north of east, right? We want to know how many degrees north of east is this plane pointing as it's flying through the air relative to the ground. So what does north of east mean? What angle is going to be theta here? Okay, good. So north of east means we're starting east and we're determining how far are we twisting north of that, from that, right? So this is going to be my theta. So, if we go back to SOHCAHTOA stuff, see if you guys remember this. If we go back to our SOHCAHTOA stuff, if I know that, for example, sine theta is equal to the ratio of opposite over hypotenuse, so down here, if sine theta equals 12/13, how could I solve for what theta is? Do you remember? Okay, we're going to take the inverse of the sine. Think back to Algebra 2 and probably last year too. What is the definition of an inverse function, right? If we throw in a little math here. So f and g are inverses if and only if. What's true? They compose to get 1. So if f of g of x is equal to, sorry, not 1, equal to x. So f of g of x equals x, and g of f of x equals x. In other words, so they undo each other. Whatever g did to x, f undoes, or whatever f did to x, g undoes, right? Inverse trig functions are the same way. So if I want to unlock the sine, I have to undo the sine, right? So I'll do a composition of inverse sine of both sides, right? What's that do? Well, it unlocks the theta on this side, and I get an answer then. Theta equals inverse sine of 12/13. That is not meaning sine to the -1 power. It's a notational thing. When we use that -1 exponent in this instance, we're talking about an inverse function and not a reciprocal, right? So on the calculator then, if I wanted to turn that into an angle, we would just do something like second sine to get inverse sine of 12 divided by 13, and that would give us back the answer 67.4 degrees for this triangle, right? And that would work for any of the trig functions. We can undo any of them by using the inverse or arc trig function. Sometimes we'll call this, you guys have probably all seen this on different calculators, it's written different ways, but inverse sine of something means the same thing as arc sine of that thing, right? It's interchangeable. So then, finishing up our problem, what are we going to do here to solve, wrong problem, there we go. What are we going to do to solve for theta? If this is our picture and that's theta, these are the two unrounded results, right? So we don't want to use the hypotenuse because that's a calculated result, right? So what's the trig function that relates these two sides? Tangent, okay? So we'd end up with tangent theta equals that ratio, right? We'll just call that r sub x over r sub, all the way around. R sub y over r sub x. Isn't that, if this is r, that's r sub y and r sub x, right? And so to find theta, I'm just going to inverse tangent or arc tangent both sides. right? So theta would just equal the arc tangent, I'll write it this way this time, of r sub y over r sub x, right? Calculator work. So we'll go back to our calculator, and I want you to see how we can just recycle all this stuff. Right, so let's go up and, first of all, let's delete that. So now we want the arc tangent of the 248 number, right? So that's going to be that one. Everybody agree? Opposite over adjacent. Divided by, what did I just do?
It didn't pick up.
It didn't pick up the other part, did it? Yeah, so let's. There, I had to go down there. So we do arc tangent of the 248 number divided by the 45 number. That one right there, right? So now if I hit enter, there's my angle. Rounded to 2 sig figs, that's what? 80, right? And so, those answers make sense? So we got that? That's pretty cool. Now, here's the thing, we're done. I'm not going to take you through any more of this. But what if how would I approach a problem like this one? What if we wanted to add up more than 2 vectors? Is that going to make it difficult? What does that do to our table?
Just adds more step.
Adds a row, right? Doing that geometrically would make it really tough. If I've got to add up vectors using law of sines and that would be very complicated, right? But if we just resolve each vector into its components, add up the x components and the y components to build our resultant vector, you could have as many rows on there as you want to. It doesn't really make it very difficult, right? See how that works? All right. Good stuff. Yep.
Here's what's-
Yes.